Computers seem smart. They can process information, play games, and even write poems. But behind all this, computers rely on a simple system logic. Logic is about making decisions based on rules. In computers, these rules are built upon a system of switches that can be either on or off. Think of a light switch, it can be either on or off. This simple idea of on and off is the foundation of how computers think. Instead of using words, computers use these on-off states to represent information and make decisions. This is the fundamental language of computers, a language of logic. This language might seem limited, but from these simple on-off states, we can build incredibly complex systems. By combining these states in clever ways, we can represent numbers, letters, and even instructions for the computer to follow. To understand how computers use on and off states, we need to learn about the binary system. The binary system uses only two digits, 0 and 1. 0 represents off, and 1 represents on. This is the alphabet of the computer. Let's take the letter A as an example. In a computer, A is not a letter but a pattern of zeros and ones. The specific pattern for A is 01000001. Every letter, number, and symbol you see on your screen is represented by a unique combination of these binary digits. These binary digits are then used to create instructions for the computer. These instructions, written in a language called machine code, tell the computer what to do. Imagine it as a recipe where each step is written in zeros and ones. Now, how do computers actually process these zeros and ones to make decisions? This is where logic gates come in. Logic gates are like tiny electronic circuits that perform basic logical operations. Think of them as the building blocks of computer decision-making. There are three basic logic gates: AND, OR, and NOT. The AND gate takes two inputs and outputs a 1 only if both inputs are 1. The OR gate outputs a 1 if at least one input is 1. The NOT gate simply reverses the input. A 0 becomes a 1, and a 1 becomes a 0. By combining these simple gates, we can create complex circuits that perform all sorts of calculations and logical operations. For example, we can create a circuit that adds two numbers together, or a circuit that compares two values and tells us which one is larger. These logical operations are the foundation of everything computers do, from running your favorite apps to powering artificial intelligence. When you write a program, you are essentially creating a set of logical instructions that the computer follows step by step. Artificial intelligence also relies heavily on logic. Machine learning algorithms, for example, use logical operations to analyze data, identify patterns, and make predictions. Every decision an AI makes, no matter how complex, is ultimately the result of a series of logical operations. So, the next time you use a computer, remember that you are interacting with a machine built on the power of logic. From the simplest calculations to the most advanced AI, it all comes down to the clever manipulation of zeros and ones, guided by the principles of logic. Think about it. What incredible machines can we build by expanding the logic of computers even further?